start. The last time we stopped in looking at the deep convection and dense water formation, and we were looking at the necessary conditions to have this kind of process. And last time I didn't mention another very important component of the dense water formation is the presence of the highly saline water in the intermediate depth. You know, when you cool the surface, the sea surface, this dense water sinks down. If reaches the layer where the density is even higher than at the surface, the density becomes even stronger, and then you have a very more violent. You are? Okay, yeah. You have even more violent sinking of the dense water, because then in that case the salinity contributes to increase of density, and therefore there is an even more efficient vertical mixing. According to some theories, this role can be played in the northern Atlantic by the Mediterranean water, because the Mediterranean water is relatively salty, and then if it spreads on intermediate layer, can reach this northern part of the Atlantic and stay there in the intermediate layer, and then even making the vertical mixing even more efficient. But this we will be talking about this later with more specifically or in more details. Here is the how we recognize the vertical mixing on the, for example, in the Labrador Sea, and where we see the temperature, salinity, and potential density in the post-convection period. That means after the convection has already taken place. And post-convection period means that there is also beginning of the surface heating. Surface heating is here expressed, as you can see, in a relatively warm surface water, and then the thermocline, but then remains as a signal. Remains as a signal this vertically mixed layer, which is, you can see here in the Labrador Sea, is up to 2.5 kilometers thick. And then you can see how huge is this area where the deep mixing takes place. The same signal you can see in the salinity, where you can see this vertically mixed layer more or less up to the same depth, and the same thing you can see in a potential density. So this is how we recognize this vertical mixing from the vertical distribution of temperature, salinity, and density. What is another thing interesting in analyzing and in what is the importance of this vertical mixing is how this process, what is the role that this process plays on the long-term circulation. As I told you before, this dense water sinks to the bottom, then spreads southward, and then there is a coming into the same area the surface warm water. So you have this form of this vertical cell of the circulation, thanks to this vertical mixing. And this cell of the circulation, if it depends only on the temperature and salinity, which is called the thermohaline circulation, will be simply a two-dimensional vertical cell. So it will be meridional, and in the surface you will be having the surface circulation flowing northward and in deeper layer flowing southward. And this is the simply thermohaline circulation, which gives up, which results in a two-dimensional circulation cell. What is important for this dense water formation is also from the point of view of the biogeochemistry of the ocean. At the surface, the ocean gets the oxygen, because the oxygen dissolves in the surface of the ocean, and the oxygen, as you know, is essential for the life in the ocean. And but obviously, again, there's just the same thing: is that deeper layers would not have the oxygen without having this vertical mixing. So the vertical mixing, especially the vertical convection, are a very powerful process which provides the oxygen to the deeper layers. And because in deeper layers, the oxygen is simply consumed. It's consumed by the activity of the bacteria. Bacteria are consuming the oxygen, and therefore the oxygen, after some time, due to the bacterial activity, will go to zero. But thanks to these kind of processes, we have the ventilation of these deep layers. The vertical convection areas are like windows in the ocean. You know, if we close this room and we only breathe without having the windows open, we will have we will consume the oxygen. The same thing is bacterial activity. Bacteria, they are using the oxygen and consuming it, and therefore, without these kind of windows in the world ocean, there will be no oxygen in the deeper layers. The same thing, this is one of the examples where the oxygen is missing completely is the Black Sea. Black Sea is, after a certain depth, there is no oxygen at all, because in the Black Sea, we should know that in the Black Sea there is a lot of freshwater discharge in the Black Sea. This creates the vertical stability of the water column, and the vertical mixing is not strong enough to create this vertical mixing, and then bacteria are used completely the oxygen, and then there is no oxygen at all after 200-300 meters depth in the Black Sea. The rest of the world ocean, more or less, this problem doesn't exist. So this is one thing. The other thing is that in the surface layer, you should know that in the surface layer, up to the depth where the light comes, there is the plankton activity. The marine plants are growing and marine plants are using and consuming the nutrients. Nutrients are the material which is used by plants to grow. That means that in the surface layer, where you have the strong growth of the phytoplankton, there is almost no nutrients, because it is consumed by plants. Therefore, there should be some vertical mixing which will enable this deep layer nutrients to reach the surface and helps the primary production, helps the production of plants in the surface layers. And these are two important aspects of the vertical mixing of the dense water formation, apart from the heat exchange between the surface and the bottom area. And so let's this is an example how the numerical simulation describes very well what is happening in the dense water formation area. This is the numerical simulation of a mixed patch induced by the extended patch of cooling applied to the surface of a resting stratified ocean. So we have a stratified ocean. At the first moment, at zero, you have the isopycnas, the lines of constant density. They are horizontal, and you apply then the surface cooling, while applying the surface cooling in the cross section. This is the cross section, like this. You can see the stars of the vertical mixing, and you can see the formation of these this eddy, this gyre around this vertically mixed area. By going on with the surface cooling, you can see that the surface mixed layer deepens due to this vertical mixing, due to the cooling which is applied. But at the same time, you can see the baroclinic instabilities which are formed around this gyre, around this gyre. And then going on, you can see that the instabilities increase, which are increasing from here to here, and at the same time there is a vertical density, vertical mixing, which reaches deeper and deeper layers and deforming the isopycnal surfaces. This is how the process looks like if you look at the by numerical model. It's important here to go and describe or follow the process very closely, because otherwise you cannot do it in a real situation. You should be present there with a very high resolution measurements, and you have to be present in a situation where the atmospheric conditions are really very hard to stay there to do the measurements and so forth. Anyhow, this is how this looks like. So what is happening here in this area here, in the central part of the area, we have this vertical mixing which brings the nutrients in the surface layer. Bringing the nutrients in the surface layer, what is happening is that there is the phytoplankton bloom, because phytoplankton in that case has the food, and therefore one of the possibilities how to recognize this vertical mixing or the dense water formation is simply to look at the phytoplankton biomass. Whenever you find the phytoplankton biomass maximum, you may be, obviously not whenever, wherever and whenever, if you have to know something about the oceanography of the area, you should know that if the area has preconditioning, has the cyclone circulation, if it has the presence of the high salinity intermediate layer, and if you have the outbreaks of the continental air, in that case you will have the dense water formation. And therefore, in that area, those areas, if you see also the patch of the phytoplankton, then you might be able to say, okay, yeah, this is the consequence of my dense water formation. And if you look at the concrete examples, if you look at the concrete example, which is going back to the Adriatic again, but nevertheless the principle is yes.
Could we exchange the lights?
Oh yes. Oh yes. This one, no. This way? Huh?
It's
Better. Okay. So this is the time evolution of the sea surface chlorophyll concentration in the area of the Adriatic. What we can see here, we can see that this is the Adriatic, as you can. And don't look at these. So the more reddish color is the higher is the concentration of the chlorophyll. The bluish means the low concentration of the chlorophyll. Chlorophyll is the color, practically the color of the seawater. And don't pay attention to this reddish area here along the coast, which are the areas where there is a strong discharge of rivers or freshwater sediments from rivers or for resuspension due to the strong coastal currents. Let's concentrate to the central part here. And these are the satellite images, and this is a specific year, but you can see these repeating practically every year. And you can imagine that doing this, the oceanographic measurements in such high resolution would not be possible with the classical instruments. You will see later when we are going to talk about the instruments how the modern instruments can be helpful in doing the high resolution, both temporal and spatial, in order to study these small-scale processes, small-scale both temporal and spatial. For example, this is the March 16, just to give you an idea of how quick, how fast are these processes. March 16, you can see what you can see is, first of all, it's very rich in the mesoscale structures. So these, you can see these eddies. You can see eddies. The general pattern is the existence of the relatively bluish area of dark blue area in the center. What that means? That means, and how do we interpret this? This means that in the center part of this area there is a strong vertical mixing. This strong vertical mixing is due to the dense water formation. What happens to the phytoplankton? Phytoplankton, even though there is enough of nutrients in the surface, this vertical mixing is so violent that it doesn't leave the phytoplankton to stay in the surface and grow. Therefore, in the phase of the vertical mixing, there is no strong phytoplankton biomass present. It's very few phytoplankton, although the nutrient concentration is rather high. So this is this thing here. But you can see this looks like very much like the satellite image what I have shown you before. There's this cyclonic circulation with number of instabilities along the border of this phytoplankton of this gyre. If you go further, which is only it's only 3-4 days after, the situation becomes completely it changes completely. This is like a negative of this one here, right? So what's happening is that here, where it used to be the minimum of phytoplankton, here is the maximum of phytoplankton biomass. And you can see also that, for example, this eddy here is here, this thing here is also here. So the pattern really remains as it used to be before. The only difference is that this pattern is this time characterized by the maximum of the phytoplankton biomass. Why so? Here, obviously, there was a strong Bora event, strong continental air outbreaks, and the vertical mixing. What's happened here is that this Bora stops. There's no any more wind-induced vertical mixing. And what happens, usually after Bora, you will see here, after Bora there is the sun is sunny. And the sunshine means that there is a surface heating, already started surface heating. And this surface heating means that there is no vertical mixing. Vertical mixing is even weaker than it would be in a normal situation. And therefore phytoplankton remains in this surface layer which is rich in light, there is enough light that the phytoplankton grow. So phytoplankton has both light and nitrates and stays in this surface layer which has a lot of light. And so there is the result of this is a strong bloom of the phytoplankton biomass in this surface layer. This is up to 100 meters, more or less, because in the first 100 meters, it's enough light that phytoplankton can grow. If we go further, which is this is 19 March, this is 4 April, again you can see that the pattern are those as they were there. There you have again this number of eddies. Even this one here, you can see this one, it more or less remains there. Also there. So these eddies, mesoscale eddies, are pretty have a lifetime here on the order of month. They are moving back and forth, but they have pretty long lifetime, and their dimension is on the order of 30 to 40 kilometers, which is much less than in the Atlantic Ocean, which you have, where we talk about an order of magnitude larger, 300 to 400 kilometers in Atlantic. The lifetime of these eddies, as I told you, is on the order of month. In Atlantic, their lifetime is on the order of almost of a year. Anyhow, from this one, respect to that one, is that the phytoplankton biomass has reduced a lot. Why it reduced? Because phytoplankton consumes very fastly the available nutrients, and therefore at a certain moment available nutrients go back to zero, and then phytoplankton starts the phytoplankton biomass starts to decrease. And finally, already April 15, there are no signs, or very few signs of this phenomena, at least as far as the phytoplankton biomass is concerned. This is an example how we can study the oceanography. We can study oceanographic phenomena, looking at the satellite information, which are not directly, but indirectly, yes, related to whatever is happening in the water column. Yeah, at the same time we were doing now serious oceanographic measurements with high resolution from ships, so we were able to confirm that the vertical structure is this, what we obtained from the satellite images. So this is the let's see what satellite images tells us for the entire Mediterranean. Is there any type of these areas also in another parts of the ocean of the Mediterranean? First of all, what here also you can have a lot of information concerning the circulation. You can see that there is along the African coast there is the relatively rich phytoplankton biomass. This is for February 1999, for example. There are a number of eddies and gyres, and then you have here the very bluish area here, which means that this area here is very poor in a phytoplankton biomass. This is what I told you before. This is the desert area, very poor in the phytoplankton, as it is very poor in a land vegetation cover, because, as I told you before, the land vegetation cover is more or less at the same latitude as the desert areas in the ocean. But this is one thing. The other thing, what really we want to do is what is happening, for example, in the southern Adriatic. This is the southern Adriatic, and you can see that in February, if you do the average February phytoplankton biomass or chlorophyll distribution, you can see that the average shows the minimum here in the center of this southern Adriatic gyre wedge, where the dense water formation takes place. This is obtained from this is the average situation, similar to this one, minimum of the chlorophyll distribution, because February is typically characterized by the strong polar wind events, and therefore the result is the minimum of chlorophyll in the center. But this is not the only area where the minimum exists. The other area where the minimum exists is this one here. This is coast of France, this is the Gulf of Lion, and another place of the dense water formation is a Gulf of Lion in the Mediterranean. So in the Mediterranean, essentially we have two areas where the deep water is formed. One is Gulf of Lion, and the other one is the Southern Adriatic. And why here? Here again you have characteristics which are, or conditions which are necessary for the dense water formation to appear. This is so that means the outbreaks of the cold continental air. So this is the Mistral, called Mistral, which is the wind coming from the Rhone River Valley. We have the cyclonic circulation which goes this way, okay? And we have also the subsurface intermediate layer salinity maximum, which is the salinity which comes from the eastern Mediterranean and passes through here, so it is present there and helps and increases, reinforces this vertical mixing. So two areas are important from the dense water formation point of view. If we go to sorry, this is April. Do I have March? No. Okay, if we go to April, April is this average situation which corresponds more to the second image. You can see the chlorophyll maximum here and the chlorophyll maximum here, even much stronger and much larger. So this is how you can recognize the dense water formation even at the monthly means, because this dense water formation, yes, it is a very short-term period, but short-term process, but it really contributes a lot to the wind mix, to the driving the vertical, the horizontal circulation. The same thing as it happens in the world ocean. As I told you before, one of the important engine of the global circulation of the world ocean is really dense water formation. Okay? So let's see what. And for example, July is there is no such features. July is a month where generally there is a low concentration of phytoplankton. Low concentration of phytoplankton because, why? Because you have the vertical stratification. The surface layer is very warm, then you have a thermocline and pycnocline, and then a deeper layer. In the surface, so the vertical mixing is relatively reduced. Much more reduced is at the minimum in the summertime because of the presence of this halocline or thermocline or pycnocline, which prevents the vertical mixing. Therefore, the phytoplankton has consumed all the nitrates all the nutrients in the surface layer, and it doesn't grow. So the result is the very poor concentration of phytoplankton in the surface layer. Okay. So let's, I found one nice thing which I would like to share with you, which is this deep ocean circulation. I would like to, this is from a NASA website. I will leave to you this PowerPoint, and where it goes in a much more details in the dense water, in a global circulation, in the possible role of the Mediterranean, and what is the Great Conveyor Belt, and what is the difference between thermohaline circulation, which is driven only by temperature salinity gradient, or and if we combine it with the wind influence, then the global Great Conveyor Belt becomes three-dimensional and not two-dimensional as it is in the case of the thermohaline circulation only. And so this is, in fact, this is how this global circulation looks like. It's not anymore two-dimensional, but it's three-dimensional. Here is the sea surface current pattern, but then you can imagine this in the vertical. So this is the third dimension, which we will be talking later. But the circulation is not so simple that you have the surface current flowing northward and then deeper there southward. You see that there is quite a complicated, complex structures which are on one hand determined by the wind, because this is the wind-driven part of this is wind-driven, combination wind-driven and thermohaline circulation, and partly is determined by the complicated coastline pattern over the world ocean. Some general characteristics of the world oceans are the presence of a number of gyres in all these oceans. So you can see this is the subtropical anticyclonic gyre, which is present both in the Pacific and the North Atlantic. You see this, the subtropical gyre in the southern hemisphere in all three oceans. Then you can see this huge current which flows along the Antarctic, which is the Antarctic circumpolar current, which is mainly wind-driven. And then you have the continuation of this. This is the Gulf Stream. You can see that you have the continuation of the Gulf Stream northward, crossing the ocean. The same thing which happens in the Pacific. And you can see here why we don't have a dense water formation in the Pacific, because there is no such a huge area around the poles where the dense water can be formed, where there is a strong heat loss from the ocean, because it's mainly land in the Pacific. Another important thing is that I will mention to you now is that not only the northern Atlantic but also the Antarctic is the dense water formation area, which happens in a different way, because Antarctic has a large shelf, and in this shelf by ice formation and by strong wind from the continent, there is then increase of salinity and decrease of temperature, and then is dense water formation which falls down along the slope of the Antarctica. So this is how these. We will come back to this pattern, to this picture few more times when we go back and try to explain the mechanisms which are really responsible to maintain this type of circulation. There are quite a number of semi-permanent currents which are circumpolar, then there is equatorial countercurrent and so forth, which are then maintained by the wind. This is the surface average circulation. That means if you go in this specific place here and you go there and do the measurement, it's not necessary that you find really that direction and that current, because this you should stay there for enough time, enough long that you obtain as an average flow in this specific areas. Okay, and this is how we why is thermohaline circulation comes into the play is this due to this surplus of heat loss over the polar areas, which then is substituted by the heat coming from south. And then you can see Atlantic Ocean each is responsible for about half of the heat transfer, because obviously it's not that only the currents, ocean currents, are transporting heat from the equatorial area to the polar area. It's also the wind, or the wind is transporting, or the circulation in the ocean is transporting the heat from the equatorial to the polar areas. And again, we are talking about both in the ocean and in the atmosphere. We are going about the residual, about mean circulation, not about these events as it is here. For example, now Bora is taking place for 2-3 days and then it stops. We are talking about the long-term average, which is responsible for this redistribution of heat between the polar and the equatorial areas. Okay, so here is the how we transfer the signal. There is a signal here. We have a signal in the surface. This signal, in some way, is transferred into the deeper layer. How is it transferred? It's transferred by the dense water formation, and so the main gyres move heat and salt. This is what we are talking about. And the resulting density variation lead to vertical flow sinking, what I mentioned you before many times. But then we have something what is called formation of water masses. Water masses are water which is characterized by the certain imprinting of both temperature and salinity. Because once this water, when the water is at the surface, it gains a certain temperature, have a certain salinity, and then sinks down. When it reaches the depth where it stays, the equilibrium depth, it has a temperature and salinity which is gained from the surface by cooling. It gained also from the salinity which gained during its transfer to deeper layers. And this temperature salinity characteristics are more or less maintained on its pathway. So we define the water mass as a mass of water which is characterized by the certain temperature salinity relationship. And temperature salinity relationship then gives rise to the specific density. Therefore, we can follow or trace different water masses by looking at the temperature salinity relationship, which is associated to these specific water masses, which has been formed in the area where this water is formed. Obviously, if you are talking about a certain salinity at a certain place, this salinity will not be exactly the same all over its path. It will be reduced or changed due to the mixing with the surrounding water, but it will have maintained part of these characteristics on its way from the area of formation, from its formation area. Yeah.
Does this occur because there is less turbulence at depth with respect to?
No, there is a turbulence, but it's the signal. Obviously, there is a turbulent exchange, and this turbulent exchange changes this temperature and salinity. But these distinct characteristics remains not exactly the same value as it was at the origin. It change becomes more and more similar to the surrounding waters, but it will keep having this. If you have the high salinity water which comes from the Mediterranean, you can follow it as a salinity maximum, not as a water of salinity 38.7, but as a salinity maximum which goes and progresses. Now we will see how it looks like in a practice. So, and this is the And density variation, the seawater, well, I showed you before this graph. This is the relationship temperature and salinity, and you can see the freezing point, and these are the lines along which the density doesn't change, although the temperature and salinity changes. This is what we call an ST diagram. And this is the distribution of the temperature salinity properties over the world ocean. And you can see that 75% of the ocean water has the temperature between 0 and 5 and salinity between 34 and 35. This is what I was telling you a few lectures before, and this is another way of presenting this. And so this is 75% of the ocean volume has 34 to 35 parts per thousand and 0 to 5 degrees Celsius. And this is another way of presenting it. This is this diagram is very nicely shows you temperature salinity diagram, and you can see this thing here is this peak between 34 and 35, and between 3 to 1, for example. And this is a very, very nice presentation, and this really shows that nearly all the water in the ocean is cold. It's cold between 0 to 5. And this is this frequency of these water masses over there. And this is again this figure what I show you, the North Atlantic Ocean circulation. Again, this is the two-dimensional picture which shows this transport in a million meter cubic per second. Million meter cubic per second. We call it Sverdrup. In oceanography, it's called Sverdrup. Sverdrup is 10 to the 6 meter cubic per second, and you can see all these numbers. Shows how much how much water is transported in what is the transport of water. Thanks to these features of these currents, that they are very narrow, relatively narrow. It's very simple also to do the measurements. You simply put your instruments across this current, for example, here, and you can measure this integrate the volume transport by this current in a specific area, because the current is very relatively narrow. We talk about 100 on the order of 100 kilometers width of this current, and therefore on 100 kilometers you just simply distribute a certain number of oceanographic instruments and do your measurements very simple, relatively simple. And so these estimates are rather precise because there are measurements which showed these numbers, confirm these numbers. And so this is here what I was mentioning a few more times. This is the thermohaline circulation, because this is its temperature determines the density, and the density. What the density determines? The density determines the atmospheric the water pressure. Water pressure is then driving this flow. You will see later how the pressure is driving the circulation. Therefore, thermohaline circulation is a simple circulation which is due to the differences in temperature and salinity between different parts of the ocean, which results then in a different density and in different pressure in the world ocean. So this is how and why this thermohaline circulation exists, really. Thermohaline circulation, as any other circulation, has to have a force. Has to have a force which drives this flow. You cannot have the driving force of the thermohaline circulation is the pressure gradient force. We'll talk about this furthermore. Okay, so now this the question, more specifically what I was talking to you before, is where does the ocean deepest water come from? The density seawater is cold and salty, as we know that, and this is formed in high latitudes in the North and South Atlantic. Again, I would like to remind you that in the Pacific cannot be formed because of the simple fact that the Pacific doesn't extend enough to the polar area. And so we have a North Atlantic deep water and Antarctic bottom water. These are two water masses. They are water masses because they are characterized by different temperature-salinity relationship. North Atlantic deep water has a different temperature-salinity relationship with respect to the Antarctic bottom water. And also they have a different density. And now let's see how it looks like. So this is again, let's look at the temperature salinity TS diagram. And North Atlantic deep water and Atlantic and Antarctic bottom water are these two asterisks. You can see that they are very close to one to another, and they are very similar in density, but they have a different temperature. They have different temperature. You can see that temperature. One has Antarctic bottom water has a lower temperature than the North Atlantic deep water, but they have a rather similar. The Antarctic bottom water has a little bit higher density. You can see how small differences are in temperature and salinity and in density between water masses. This is why we do have to have a high accuracy of the measurements of both temperature and salinity. So all of this enormous amount of water is concentrated in this part of the TS diagram, or the diagram showing the relationship between temperature and salinity. And this is the schematic presentation what I already showed you before. And Atlantic, North Atlantic, Antarctica, and these are the sinking of two dense water. And then you can see it's a pycnocline layer. Is this what I was talking to you? This is a permanent pycnocline which is present all over the year, except in the polar areas where the vertical mixing destroys this layer. And now let's see North Atlantic deep water. So this is the Atlantic Ocean, and we have North Atlantic deep water, and we have Antarctic bottom water. And this is how they spread. Here is the Denmark Strait, and the North Atlantic dense water is formed in Labrador Sea there, and then it flows over the cell and sinks down because it is very heavy, sinks down to a depth where it reaches the equilibrium, where it has the neutral buoyancy, where it has a density equal to the surrounding water density, and it covers the entire parts of the Atlantic, for example, in this specific case, while the Antarctic bottom water is spreading from the Antarctica, but they are below the North Atlantic deep water because it has a higher density than the Atlantic water. So you have already two-layer structure in the bottom layers of these two waters because they are of a slightly different density. Obviously, you can see these things. That means that they are mixing between themselves, and the interface between the two water masses is not so well defined. It's a smooth passage from one seawater to another, simply because of the vertical mixing, which is especially important in the slope area where this water sinks down, there is a lot of turbulence, and so there is the vertical mixing, like here, like this area where the water sinks through the bottom slope. And so this is the no, sorry, I was going in the wrong direction. Okay, so this is deep and bottom potential sites and how this water is spread horizontally. Before we have looked into the vertical transect, this is how the Antarctic bottom water which is formed in Weddell, Ross, and Adelie Sea, which show this area here. You can see 3 areas where this dense water is formed on the Antarctic shelf. And you can see more or less how this water spreads into 3 oceans, and how we obtain this pattern, how we obtain this extension, spatial extension of this water, simply by defining water masses from their temperature salinity relationship, and we follow it by doing the measurements in the deepest layer. And this is how this pattern looks like, and you can see that in some parts it reaches, this is the Gulf of Mexico, it even reaches the northern hemisphere area. So this is the, and what about the North Atlantic deep water is this thing here, which is formed in this area here, and so this is how their horizontal extension looks like. This is the right direction. Yeah. So the major site of the Antarctic bottom water is the Weddell Sea, and it flows northward as deepest layer in Atlantic, Pacific, and Indian Ocean basin. Antarctic water is very extensive. It goes in the Pacific 50 degrees and in Atlantic 45 degrees. This is its speed. Its speed is 0.03 to 0.06 kilometer per hour, and the time associated to this current flow is 250 years. So 250 years is more or less the residence time. The time needed for the bottom layer to be renewed by becoming this Antarctic dense water. So, and this is simply calculated from the average speed and from these 10,000 kilometer extension of this Antarctic water. Yes. Okay, go ahead. And the North Atlantic dense water, deep water, is formed in coastal Greenland, Labrador Sea side. The formation comprises about 50% of the deep water to the world ocean, and sinks directly into the western Atlantic. So it goes below the Gulf Stream in a deeper layer, goes down southward, and North Atlantic periodically spills over silts into the North Atlantic. So it has the silts in the North Atlantic, which sometimes it spills over, because these silts separate the formation area from the rest of the Atlantic, and it spills over. So this is the description of the North Atlantic dense water, deep water, sorry. And so this is the how we define these water masses and how they are present and spread. You can see there are a number of water masses which are defined on the basis of their temperature, salinity characteristics, and or density. And all these, you don't have to remember all these acronyms, because you have the Atlantic Ocean, Pacific, and Indian Ocean, and For example, this little thing here is the Mediterranean intermediate water. So this is the relatively salty, but at the same time relatively high temperature water, and this is why it stays in the intermediate layers. Otherwise, if it were by salinity, it would sink down directly. But since it is relatively warm, stays in the intermediate layer. Then you can see North Atlantic dense water, which goes down, and this is Antarctic bottom water, what we were talking about, and this is North Atlantic water, which stays above the Antarctic bottom water. These are the surface water, which are above a picnic line, and the similar or equivalent situation is in other oceans. Okay. So now let's see. What is how come this water from the Mediterranean has this high salinity? It has high salinity because we have essentially two types of the semi-enclosed basins. Mediterranean is a semi-enclosed basin. It's semi-enclosed basin because it's connected with the Atlantic by the Gibraltar Strait. Relatively narrow, only 40 kilometers, relatively shallow, only 400 meters, while the Mediterranean has the depth of about 5,000 meters maximum, 5,000 meters, 5 kilometers. But from the point of view of oceanography, it goes to this category here, which is the evaporative basin. Evaporative basin or condensation basin means that the evaporation is stronger than precipitation, and therefore the sea level in this kind of basin is lower than at the open ocean. And also, what is important is that there is a higher density and higher temperature and high salinity here than outside. As a result of that, this concentration basin release the relatively high density water into the deeper layer, and has as a compensation the surface water coming from the neighboring fresher or lower salinity ocean. There is another asymmetric part of the Mediterranean type of Mediterranean Sea or semi-enclosed sea, where the evaporation is lower than the rainfall and river input, and then you have the sea level in it is higher. The salinity here is higher, lower than in a neighboring ocean, and then this type of basin releases the fresh water in the surface level, lower salinity water and fresh water, and as a compensation you have the inflow of saltier water in a deeper layer, which compensates for this outflow. So these are two types of semi-enclosed seas. The Mediterranean makes part of this. Makes part of this group of the Mediterranean seas or semi-enclosed seas. And in a practice, what it looks like if you do the measurements across the Gibraltar Strait. So you imagine that you are crossing the Gibraltar Strait from the Mediterranean, which is on the other side, to the Atlantic, which is on the left-hand side. The isohalides, which are these lines here, have this shape, and this is what you remember that I was talking to, that the signal of the high salinity you can see from or water masses you can see from the higher from the specific relationship between temperature and salinity. In this specific case, the main signal is in the salinity. And higher salinity, you can see that this water of relatively high salinity, which has 38 parts per thousand, has this salty salinity. exits through Gibraltar. This is the Gibraltar Strait, and then sinks down in the Atlantic. Why it sinks down? Sinking down because it's heavier than the Atlantic water. So it will sink down as long as it reaches the equilibrium. It reaches the area where its density is equivalent more or less to the density of the ambient water. At the same time, as a compensation flow, you can see the inflow of the Atlantic water entering the Mediterranean. So, because obviously here at this specific position, or in the Gibraltar Strait, the water exchange rate has to be zero. The transport has to be zero. Sum of inflow and outflow has to be zero. Otherwise, the sea level would be rising or sinking or decreasing continuously, which is not allowed. So, due to simple continuity, the inflow and outflow has to be zero. But we have to take into consideration that from the Atlantic, according to measurements, we have about 1.107 million meter cubic per second, which enters from Atlantic with this salinity here. And then we have in the Mediterranean, we have precipitation is 0.027 and the river runoff is 0.011. And you can see that evaporation is larger than both precipitation and evaporation. So this loss of water due to the stronger evaporation with respect to the precipitation has to be compensated by the larger inflow than outflow. And in fact, this is from the Atlantic, this is to the Atlantic, and the difference between the two. And so you have to have the sum of these has to be equal. And in fact, this is so more or less we have around 1 million meter cubic per second which enters or exits from the Atlantic into the Mediterranean in order to compensate for these differences between evaporation and precipitation, or in order to exchange, to exchange the water between the two basins because of differences in the temperature and salinity, but mainly in salinity, because what determines really the oceanographic characteristics of the Mediterranean are differences in temperature, in evaporation and precipitation. So that means the process which determines the salinity, and not in such an important degree temperature. Okay, so this is how it looks like. And this is how, if we extend our transect or our cross section between the Eastern Mediterranean and the Atlantic Ocean, which is this is Gibraltar Seal, this is the Sicily Seal, and you have here the Western Mediterranean, and here is the Eastern Mediterranean. We are more or less here. And so you can see how these Atlantic surface fresh water goes this way. Obviously, you can see that there is an increase of salinity, continuous increase of salinity of this Atlantic water, simply because it exchanges it mixes with the surrounding ambient Mediterranean water. And then you have here the huge parts of the Mediterranean which are occupied by the dense salty water. And dense, this water is dense because it's very salty on one hand, and on the other relatively saltier than the Atlantic. but it's also colder. It's cold because of its formation sites, Gulf of Lion and Adriatic Sea. The water which is present here, all this water is what has been formed in the two sites, the Gulf of Lion and the Adriatic, where Adriatic mainly occupies this part, and the Gulf of Lion water occupies that part here. And so this dense water spills over the Gibraltar Sill and goes into the Atlantic. And here we have this tongue of the Mediterranean waters. What has been noticed is not simply a kind of river or a tongue, continuous tongue. It's a series of eddies which are formed at the Gibraltar Strait, and they are progressing into the Atlantic. So these eddies are traveling, and they are on the order of 100 kilometers, and they are present and they can be seen also from the satellite, because they leave the signal at the satellite surface. And these eddies, because they are on the origin of Mediterranean, they are also called the Meddies. Meddies. And they take this salty water from the Gibraltar Strait into the center of the Atlantic Ocean. But if you do the average on long term, you will obtain this tongue. You will obtain this continuous tongue flow of this Mediterranean water. And here is how it looks like, this tongue, how it looks like. Here is this tongue, and you can see this 36.5. So it has larger salinity on both sides, both of deeper and a shallower layer in the Atlantic. And why it stays there? It stays there because in the vertical the density increases with depth. But since the temperature of this Mediterranean water is higher than the surrounding water, the density here is higher than here, but lower than here and higher than here, because the temperature is higher here, although the salinity is higher. So this is how schematically this looks like. And this is how this Mediterranean water horizontally spreads over the Atlantic, and you can see this dark green things, and you can see how it spreads all toward the American continent. This green area are where the temperature in the Atlantic at 1,000-meter depth. See how this is the signal associated to the Mediterranean water in temperature. The Mediterranean water has higher temperature, although it's not the same temperature as it used to be when it exits the Gibraltar, but it has higher with respect to the ambient Atlantic water. And you can see that it spreads first westward, but then it sinks, it extends also northward. So it has a two main direction of the extending in the Atlantic, and might be that it participates in the dense water formation in the polar areas. To what extent it is important, nobody knows. For the moment, it is unknown. And this is that's the salinity. Salinity more or less shows the same feature, shows this extension toward the American continent, and it's extending toward the polar area. So this is it's quite an important area covered by this Mediterranean water. Okay, so this is a deep Atlantic circulation, how it looks like. So you have the Antarctic circumpolar water which is formed in the Antarctic. You can see this, if you look, we did the cross section, north-south cross section, and this is how the Mediterranean water looks like, a blob of this water at a certain depth, around 1,000 to 2,000 meters. And then you have Antarctic intermediate water, and then you have the surface circulation. And so this is more or less how it looks like. And this is the Atlantic meridional overturning circulation, because it has this overturn, it has this surface to deeper layer mixing, and then this meridional overturning circulation. So this is the MOC. You will okay. So now we come to the great conveyor belt. Surface water highlighted forms deep water. Deep water sinks and flows at depth throughout the major ocean basins, and this water, deep water, upwells to replace the surface water that sinks in polar areas. This is another important process. Not only the vertical mixing or the vertical sinking of water, but there is also the upwelling, where the deep water is brought to the surface, which brings its characteristics into the surface. And surface flow must flow to high latitudes to replace the water sinking in polar areas, because since the water is sinking in polar areas, something has to replace it. So, and this idealized circulation is called the great conveyor belt or thermohaline circulation, where we simply assume that the only forcing is the temperature salinity differences or the density differences. Okay, so I will skip over this thing, and this is that's the great conveyor belt, thermohaline driven, what I've already mentioned to you. And now this is one more important aspect which I will just like to touch, is that on long time scale average ocean temperature affects the climate. And most water is in deep ocean. The very thin surface layer is the one which is in contact with the atmosphere. And that's another important thing. The average temperature of ocean is functional process of both water formation and transport of water around the ocean basin, because most water is in deep ocean, and process and average temperature of the ocean depends on this major volume of the water which is present in deep part of the ocean, whose temperature depends on the process of bottom water formation transport, or bottom water formation, and on transport of water around the basin. Okay, so these two processes are determining the temperature of the world ocean, determining the major part of the volume of the world ocean. And deep water recycle time is around 1,000 years. So if you increase or decrease or change the temperature of the dense water form, the response time of the major part of the water volume will be around 1,000 years. So this is on one hand it's very important number. And this is one nice picture, which shows that how the ocean is responsible for warmer temperature on the west coast of continents compared to the east coast. This is the warmer and this is cooler. You can see that this switching between warmer and cooler, and difference of winter surface temperature from latitudinal average. If you this is that's a nice illustration how the same latitude, typical summer day in Newfoundland, you can see how much snow is it, and typical spring day in a Torbay in southwest England. And this is something which is due to the ocean circulation, the fact that the heat is transported toward England and not toward the Canada coast, thanks to the Gulf Stream, which leaves the coast of America. Now we are coming to another important aspect: is what could happen if the Atlantic MOC changes, and there is these are the results of the numerical model. You can see that these numerical models are still in a very early phase, and you can see how large is dissipation between different models. All these curves are different models. What can be generally seen is the decrease of the Atlantic MOC. These are the sphere groups, and you can see how all the models agree that there will be a decrease of the intensity of the Atlantic circulation. And these are the observations. You can see that the observations, as I told you before, the observations are relatively easily organized, because we just make a cross section across the part of the Gulf Stream, and do our measurements and find out what is the long-term changes. And we have now like 20 years of these measurements, which shows on one hand, obviously, 20 years is not enough to get the trend, to get the reduction of this, the MOC reduction, because there is a long-term changes of this circulation. But anyhow, this is something which is important to take into consideration when we talk. And what would be the possible impacts of the shutdown or reduction of the Mediterranean overturning circulation? Meridional overturning circulation in the Atlantic, which is, as we have seen, this contributes a lot to the differences, asymmetry between the climate east-west. We will have a reduction in runoff and water availability in southern Europe, major increase in snowmelt, flooding in western Europe. So because the changes on the temperature of the sea surface, or sea surface temperature of the ocean, will be influencing the formation, for example, of the cyclonic activity over the northern Europe. And this will then contribute to changes in water availability of southern Europe, because it will be changing the rainfall and so forth. Then there will be increase of sea level rise on the western European and Mediterranean coast. This is partly due to the increase of the temperature, and then stretching of the water column on one hand. On the other hand, it will be an increase of the freshwater availability and melting of ice over the northern areas, and this will be another process which will contribute to increase of the sea level. There will be a reduction in crop production with impact on food prices, because of less availability of the water. Last time, a few days ago, I read that climate change is influencing a lot on coffee. There are a number types of coffee which cannot survive these changes, this extreme climatic features. So drink your coffee today, not live for tomorrow. Changes in temperature affecting ecosystems in Western Europe and the Mediterranean, like affecting biodiversity, forest product, and food production. Well, okay, disruption to travel opportunities, increase icing in the northern ports and seas. This is something which is very, very important, because that means that the maritime traffic will suffer a lot. Changes in regional pattern of increase versus decrease of cold and heat related death and illnesses. Movement of population to southern Europe, everybody will be coming here. Need to refurbish infrastructure towards Scandinavian standards and so forth. Okay, so these are a number of consequences which are directly or indirectly related to the meridional overturning circulation reduction, or even block. Okay, I will just this one, and then we will stop. So deep ocean water properties in circulation play a critical role in Earth system climate, because of the simple fact that the major ocean volume, water volume, is there. Modulates climate on long time scale, hundreds to thousands of years. The ocean has enormous capacity to absorb and release greenhouse gases. This is another thing what we'll be maybe touching a little bit upon in the coming hours. So the temperature and composition of seawater circulating through the deep ocean is vitally important in assessing long-term climate change. So what we see now, what is happening, for example, in areas of the dense water formation, if we notice some increase or decrease or changes in the thermohaline characteristics of the dense water formed in the Atlantic or Antarctic areas of formation, we will be sure that this kind of signal will then be felt over the major part of the world ocean within the next hundreds and thousand years. This is very important. So that's very important to do the observation, do the monitoring of whatever is happening in the world ocean. Okay, so this is just give you a flavor of what is the importance of